This is part 2 of a series on Word2Vec. In this video, we will implement a CBOW model. This video was produced in Korean and translated into English, and the voice was generated using text-to-speech. In the previous video, we looked at the basic structure of CBOW and skipgram models. In this video, we'll look at subsampling of frequent words and implement a simple CBOW model in Keras. Section 2.3 of this paper, by Tomas Mikolov et al. In 2013, presents a technique for subsampling frequent words. In very large corpora, the most frequent words can easily occur hundreds of millions of times, e.g. in, the, and a. Such words usually provide less information value than the rare words. For example, while the skipgram model benefits from observing the co-occurrences of France and Paris, it benefits much less from observing the frequent co-occurrences of France and the, as nearly every word co-occurs frequently within a sentence with the. To counter the imbalance between the rare and frequent words, the authors of this paper used a simple subsampling approach. Each word WI in the training set is discarded with probability computed by the following formula, where f of WI is the frequency of word WI in the corpus, often expressed as the fraction of occurrences of Y relative to the total number of words. And T is a chosen threshold, typically around 10 to the power of -5. They chose this formula because it aggressively subsamples words whose frequency is greater than T while preserving the ranking of the frequencies. If f is greater than t, this becomes smaller. And if we take its square root, this term becomes even smaller. Then the discard probability increases, and the word WI will be discarded with a high probability. Although this formula was chosen heuristically, it works well in practice. It accelerates learning and even significantly improves the accuracy of the learned vectors of the rare words. The probability of keeping a word WI is as follows. We can also use the following formula. This formula appears in the original C code developed by Tomas Mikolov and his colleagues at Google, where the sample is T, and vocab word CN divided by train words is f of WI. Let me give you an example. Let's say a word appears 2,000 times in a corpus, and the corpus contains a total of 1 million words, and T is set to 10 to the power of -3. Then f is computed as follows. The keeping probability calculated using the above formula is 0.71. This means that we use 71% of the word WI and discard the remaining 29%. If we calculate it with the formula below, we get 1.21. This can be greater than 1, meaning 100%. This means that we use 100% of the word WI. The formula above discards more words than the formula below. We will use this formula for implementing Word2Vec models. Next, before implementing the CBOW model, let's first create a dataset. We'll use the Gutenberg dataset provided in NLTK. This is a collection of public domain literary texts made available through Project Gutenberg. NLTK includes a small selection of texts from the Gutenberg dataset. Download the Gutenberg corpus using NLTK. Next, we define the stop words. Stop words are very common words like the, a, and is that have little meaning on their own, so we will remove them from the corpus. By removing these words, the model can focus on more significant words and handle various tasks more efficiently. The stop words provided by NLTK are as follows. We can add any words we want here like this. Next, we get a list of file names from the Gutenberg text files. This list contains 18 text file names as follows. Next, let's count word frequencies in these text files. Get the file names one by one from the list of file names, and load the text contents of each file. Then we split the text into a list of individual sentences, and we split each sentence into a list of individual words. Next, remove the stop words from the word list. If a sentence contains more than 5 words, count the word frequencies. Otherwise, discard the sentence. And we save these words in a list called List Sentences 1 for later use. The 10 most frequently used words in this corpus are as follows. The most frequently used word is shall, appearing over 10,000 times. The second sentence in this list is as follows. The number of unique words is 51488, and the number of total sentences is 70307. The total sum of word frequencies is around 1 million. Now that we have counted word frequencies, we can subsample the data. Write a function that calculates the probability of keeping a word using the following formula. We read each sentence in List Sentences 1, one by one, and perform subsampling for each word in the sentence, as follows. And we save the sentences for which subsampling is completed in List Sentences 2. The second sentence of List Sentences 1 is as follows, and the second sentence of List Sentences 2 is as follows. You can see that the word little has been removed due to subsampling. Next, we use Keras' tokenizer class to tokenize the list of subsampled sentences. The FitOnTexts method builds and updates the internal vocabulary of the Keras tokenizer class based on a list of sentences. This method creates the vocabulary index based on word frequency. The word index attribute of the tokenizer object is a Python dictionary that maps words to their corresponding integer indices. This dictionary is as follows. It has words as keys and their assigned integer indices as values. The index starts from 1. Index 0 is reserved for pad. If we switch the keys and values in this dictionary, it would be as follows. This dictionary allows you to look up words using integer indices as keys. And the text-to-sequences method converts the texts into sequences of integers in this dictionary. The sequences converted to integers are as follows. Finally, store the vocabulary and the sequences for later use. Now that the data preprocessing is complete, let's implement the CBOW model. First, load the preprocessed Gutenberg corpus. The vocabulary and a list of sentences will be loaded. The first sequence in the list of sequences is as follows, and the vocabulary is as follows. Next, create a training dataset with 5 grams. We read each sentence in the sequences list one by one and generate 5-gram sequences, overlapping contiguous sequences of 5 tokens. NLTK's ngrams class makes this easy. It extracts 5 consecutive tokens using a fixed sliding window. Here C is the center word or target word, and the rest are surrounding words, i.e. context words. Context words are the inputs to the CBOW model, and the center word is the desired output of this model. In this way, we generate a training dataset for the CBOW model. The input to the model, xtrain, consists of 4 context words as follows, and the desired output of the model, ytrain, consists of a single center word or target word as follows. nvocab is the vocabulary size, and nemb is the size of the word embedding vector, which is set to 32. Now let's create a CBOW model. The structure of the CBOW model we looked at in the previous video is as follows. First, we create a custom layer for the word embedding layer. Although the embedding layer provided by Keras makes it easy to implement the CBOW model, we created a custom layer like this to better understand how this layer works. The input dimension and embedding size are fed into this layer. The input dimension is the vocabulary size. The embedding size is the size of a word vector, which in our case is 32. Create a word embedding matrix C using TensorFlow's variable. During backpropagation, each element of this matrix will be updated. This model can then generate the appropriate embedding vectors for each word. The call method receives the indices of the words entered in the input layer. Select the row vectors corresponding to the input indices x in matrix C. This is the table lookup in C process. And then return the selected row vectors. Now let's create a CBOW model. Create an input layer and the custom embedding layer we created above. The output of this layer is the tensor XMB of size 4 by 32. 4 is the number of context words input to the input layer, and 32 is the size of the embedding vector. None is the batch size. Next, we take the average of the 4 word embedding vectors. Finally, we create a softmax or hierarchical softmax output layer. The number of neurons in the output layer is the size of the vocabulary. The authors of the paper used a hierarchical softmax output layer. But here, we will use a softmax output layer to simplify the model. We'll look at hierarchical softmax in later videos. create a model and compile it, and fit the model to the training dataset. Next, plot the loss history to see how the model learns and how the loss decreases during training. You can see that the loss decreases like this during training. Next, we take the word embedding matrix C from the embedding layer of the trained model. For example, the embedding vector for the word mother in this matrix is as follows. Next, we will represent the 32-dimensional embedding vectors in a 2-dimensional space and check whether words with similar meanings are clustered close together. Transform the 32-dimensional embedding vector into a 2-dimensional vector using PCA. And we represent the 2-dimensional embedding vectors of the following words in a 2-dimensional space. Let's check the results. Flower names are distributed here. Country names are distributed here. And words related to family are distributed here. You can see that words with similar meanings are grouped together in this space. In this video, we implemented a simple CBOW model in Keras. In the next video, we will implement the skipgram model.